Stars at the outer edge of galaxies appear to be moving far too fast for the gravity we can actually see. Under known gravitational expectations, those stars should drift outward or break away entirely, yet the galaxies remain stable. Astronomers first mapped galaxy rotation curves expecting orbital speeds to decrease with distance from the galactic center. Visible matter becomes thinner toward the outer regions, so the gravitational pull should weaken in the same direction. Instead, the observed velocities remain unexpectedly high across enormous galactic distances. The anomaly does not appear in a single galaxy or a rare observation. Rotation curves across many galactic systems repeatedly show the same pattern, suggesting the mismatch is tied to the structure of galaxies themselves rather than local measurement error. Current models indicate that visible stars, gas, and dust cannot generate enough gravitational influence to hold those outer regions together. The observed motion implies the presence of additional mass, yet telescopes detect no corresponding luminous structure surrounding the galaxy. This leads to the proposal of an invisible mass envelope extending far beyond the visible galactic disk. The structure is referred to as a dark matter halo because its gravitational effects appear measurable, even though the halo itself remains observationally hidden. The halo is not inferred from direct imaging. It emerges from gravitational behavior that appears inconsistent with the amount of detectable matter inside the galaxy. The system therefore depends on a component whose existence is suggested through motion rather than observation. A familiar gravitational expectation begins to fail at galactic scale. In smaller systems, orbital velocity usually decreases as distance from the central mass increases. Galaxy rotation curves instead flatten outward, producing a pattern that current visible matter models cannot naturally reproduce. The contradiction becomes sharper when comparing inner and outer galactic regions. Dense central regions behave relatively close to expectation, but outer stars continue moving with nearly the same rotational speed despite being immersed in far weaker visible gravity. This creates a physical imbalance that should destabilize the galaxy over time. If only visible matter were present, many outer stars could eventually escape the system entirely. Their continued confinement implies an unseen gravitational influence acting across vast galactic distances. The invisible halo hypothesis attempts to restore causal consistency by surrounding galaxies with far more mass than can currently be detected directly. Current models suggest the halo may extend well beyond the visible boundaries of the galaxy itself, forming a larger hidden structure around the observable system. Yet the proposed solution introduces a second uncertainty. The gravitational effects appear measurable, but the underlying mechanism producing the hidden mass remains unknown. The system therefore shifts from a motion problem into a missing data problem. No telescope has directly observed the halo as a visible object. Its existence is inferred indirectly through rotational behavior, gravitational interaction, and large-scale galactic stability. The central evidence is therefore observationally incomplete from the beginning. The anomaly also affects how total galactic mass is estimated. Measurements based only on visible matter consistently produce values too small to explain the observed rotational speeds. Additional unseen mass appears necessary to close the gap between prediction and observation. This creates a cognitive contrast between what galaxies look like and how they behave. Visually, galaxies appear dominated by luminous stars concentrated toward their centers. Dynamically, the majority of their gravitational influence may exist in regions that emit no detectable light at all. The hidden structure appears to govern the observable structure rather than the reverse. Visible galaxies may only represent a small embedded region inside a much larger gravitational system that cannot currently be mapped directly. The evidence gap becomes more severe because the missing component interacts weakly, if at all, with ordinary electromagnetic observation. Light reveals stars, gas clouds, and energetic regions, but the proposed halo remains effectively invisible under the same observational methods. Astronomers can therefore measure the consequences of the system more clearly than the system itself. Rotation curves provide indirect evidence of gravitational influence, yet they do not reveal the physical composition of whatever generates that influence. Alternative interpretations have occasionally questioned whether gravity itself behaves differently at galactic scale. If gravitational laws shift under extreme distances or low accelerations, the anomaly might emerge without requiring large amounts of hidden matter. But this interpretation introduces another contradiction. Modified gravitational behavior must still reproduce the large-scale consistency observed across different galactic environments, while remaining compatible with other gravitational measurements already verified elsewhere. The invisible halo model avoids changing known gravitational structure, but it depends on a dominant physical component that has not been directly identified. The modified gravity interpretation reduces the need for hidden mass, but risks destabilizing existing gravitational frameworks that currently explain many other systems successfully. The deeper uncertainty emerges from how much of the galaxy may be physically inaccessible to direct observation. Most visible matter occupies only a fraction of the gravitational environment implied by rotational measurements. The majority of the system may therefore remain structurally hidden. This transforms the anomaly from a local observational problem into a galactic-scale boundary of knowledge. The visible galaxy behaves as though embedded inside a larger invisible architecture, whose physical properties remain incomplete. The longer rotation curves are studied, the harder the anomaly becomes to dismiss as accidental noise. Independent observations repeatedly converge toward the same mismatch between visible matter and gravitational behavior, reinforcing the possibility that something fundamental is still missing from current galactic models. Yet the missing data prevents a complete causal closure. The system behaves as though an invisible mass envelope surrounds galaxies, but the physical nature of that envelope remains unresolved, leaving the mechanism behind the observed stability only partially explained. The uncertainty spreads beyond individual galaxies because the rotational anomaly appears across systems with very different visible structures. Spiral galaxies with varying sizes, densities, and star distributions still produce unexpectedly similar rotational behavior in their outer regions. The hidden dependency therefore appears tied to galactic-scale structure itself, rather than isolated local conditions. The farther observations extend from the visible galactic center, the less directly measurable the governing mass becomes. Outer rotational stability increasingly depends on a gravitational component that cannot be mapped through ordinary luminous observation. The system grows more dependent on invisible structure precisely where visible structure becomes weakest. This creates a widening observational asymmetry. The region exerting the strongest unexplained gravitational influence may also be the region with the least direct detectable matter. Current models suggest the halo must remain dynamically stable across enormous distances over long cosmic timescales. Small inconsistencies in gravitational distribution could gradually distort galactic rotation, alter orbital coherence, or destabilize outer structures. Yet many galaxies appear to preserve remarkably organized rotational behavior, despite the inferred hidden complexity surrounding them. The hidden mass envelope therefore cannot behave as random gravitational noise. Whatever generates the anomaly appears distributed with enough consistency to maintain large-scale structural order, while remaining effectively invisible to direct observation. This tightening constraint produces a second-order consequence. The more precisely galaxy rotation curves are measured, the narrower the acceptable range of hidden gravitational behavior becomes. The invisible structure must simultaneously explain high rotational velocity, large-scale stability, and broad consistency across different galaxies without introducing obvious observable contradictions. The anomaly becomes harder to isolate because visible matter still participates in the same system. Stars, gas clouds, and luminous galactic regions continue interacting with gravity normally, but the total gravitational outcome exceeds what those visible components should produce on their own. That overlap obscures the exact boundary where visible gravitational influence ends and hidden influence begins. Current observations reveal combined motion, not clean separation between known and unknown mass contributions. As measurements improve, the hidden structure appears less like an isolated correction and more like a dominant component of galactic architecture. In some models, visible matter may account for only a minority of total galactic mass, meaning the observable galaxy could exist inside a much larger, unseen gravitational framework. This creates a scale escalation that alters the interpretation of the galaxy itself. The luminous spiral structure commonly identified as the galaxy may only trace a thin, visible layer embedded within a far larger invisible system. The measurement problem deepens because rotational velocity can be observed directly, but mass distribution must be inferred indirectly from motion. The anomaly therefore depends on reconstructing hidden structure from its consequences rather than observing the structure itself. Any uncertainty in that reconstruction propagates outward into the entire galactic model. A small deviation in inferred gravitational distribution can produce large differences across galactic scale rotational predictions. Tiny uncertainties near the inner system amplify into major discrepancies at extreme distances, especially where visible matter becomes sparse. This amplification effect increases the importance of missing data. The outer regions of galaxies become both the strongest evidence for the hidden halo and the least directly observable part of the system. One unresolved tension remains particularly difficult to close cleanly. If the hidden mass envelope dominates galactic gravity so extensively, its large-scale distribution should leave consistent structural signatures across different systems. Yet the inferred shapes, densities, and boundaries of halos remain difficult to constrain precisely from rotational data alone. The anomaly therefore resists collapsing into a single stable physical picture. Motion strongly suggests hidden structure, but the exact configuration of that structure remains partially indeterminate. The deeper the halo extends beyond visible galactic regions, the more its influence propagates into surrounding space. Outer stars may only represent the innermost visible consequence of a gravitational field extending far beyond the luminous edge of the galaxy itself. This propagation changes the scale of the mystery. The anomaly is no longer confined to stellar motion near visible structures, but may involve enormous invisible distributions shaping galactic behavior across vast distances. The system also develops a hidden dependency problem. Current galactic models increasingly require assumptions about unseen mass distribution before rotational behavior can be predicted accurately. The explanatory framework therefore depends on variables that cannot currently be measured directly. That dependence creates a boundary condition in observation. Motion remains observable. Gravitational effects remain measurable, but the underlying source responsible for those effects remains structurally incomplete inside the model itself. The anomaly sharpens further because gravitational behavior appears internally coherent, despite the missing mechanism. Galaxies do not behave chaotically or randomly. Their rotational structure follows stable, repeatable patterns that imply an organized underlying system still hidden from direct observation. The visible galaxy therefore behaves as though embedded inside a larger physical architecture, whose dominant mass component remains observationally absent. The more stable the rotational patterns appear, the harder it becomes to dismiss the hidden structure as a temporary modeling artifact. Yet the hidden halo remains inferred rather than directly resolved. Current models can approximate its gravitational consequences, but they still cannot fully explain what the invisible mass envelope physically is, how it formed, or why its influence appears so consistently tied to galactic rotation across the observable universe. Galaxy rotation curves no longer appear to be isolated observational errors. The repeated consistency of the anomaly across galactic systems has narrowed the problem into something more structurally difficult. Either a major portion of galactic mass remains invisible, or current gravitational interpretation becomes incomplete at extreme scale. Neither explanation fully closes the system. The hidden halo model resolves part of the contradiction by restoring enough gravitational influence to explain the observed motion of outer stars. But the solution depends on a dominant physical component that still cannot be directly observed, measured cleanly, or fully characterized beyond its gravitational effects. That leaves a boundary inside the model itself. Motion can be tracked, rotational stability can be measured, yet the mechanism producing the missing gravitational influence remains physically unresolved, forcing current galactic models to rely on a structure that is still largely inferred rather than understood. The deeper observations extend into the outer regions of galaxies, the more the visible system appears incomplete on its own. What once looked like isolated collections of stars may instead be only the luminous surface of a much larger invisible architecture surrounding them. Current models can describe how galaxies behave under the influence of this hidden structure with increasing precision, but they still cannot fully explain what the structure actually is, why it forms so consistently across galactic systems, or where the boundary of its influence truly ends.